Okay, in this video, Introduction to Imaginary Numbers, I want to do a couple of things. I want to talk about what we might use them for and why we would even care about imaginary numbers. I want to show you a little bit of the arithmetic that we can do with them, which is just like the arithmetic that we can do with other numbers. But sometimes you guys freak out about that, so. And lastly, I'm going to actually show you solving for some imaginary roots of quadratic, which is where you'll see this come up a lot. All right, friends. So your book does a lot of things that are great, I'm sure. Wonderful, whatever. But wow, it is a travesty what it has done to imaginary numbers. Because it basically just tells you what they are, and then it doesn't tell you the crazy story behind it, which I'm going to make you guys learn about because it's amazing. Anyways, imaginary numbers basically deal with this giant hole in mathematics that we had for a really long time, which is this, that the fundamental theorem of algebra, which is just a really excessively named thing, but whatever, it's the name, says that anytime you have a polynomial, so like x cubed plus 4x minus 2 equals 0, or x squared equals negative 1, or x, well, I probably shouldn't use that. Let's just say that's a 4. 3x to the 17th minus 2 equals 5. I don't care. It really doesn't matter. It says that the highest degree, so the highest degree here is 3, the highest degree is 2, the highest degree is 17, that the highest degree determines the number of roots that the problem is going to have. You guys might think about this when you did quadratics as zeros. So this, x squared equals 4, has 2 zeros. It has a 0 at 2, and it has a 0 at negative 2. And if you guys are graphing that on a lovely Cartesian coordinate grid, you'd say like, okay, here at negative 2 and here at positive 2, I know this parabola is going to have a 0, this guy. So like 0 here, 0 here, and those are the roots, and there have to be 2 roots here. But we run into a problem when you graph things like x squared plus 3 equals 0, because when you graph that guy, it looks like this, and you're like, well, the fundamental theorem of algebra tells me this thing has to have 2 roots, and like, dude, I don't see them. So that's where imaginary numbers come in, and then it becomes like a pretty sweet, awesome thing. It's crazy that we sort of just accepted that this was a real thing, and when we did, like, it opened up this huge, amazing part of mathematics. Man, math is awesome. I love it. Okay. Before we get into what we're going to actually be using this for, we need to do a little bit of imaginary arithmetic. And of course, I've already screwed up and I put that too high. It's fine. Whatever. We'll deal with it. So this is the fact that we're working with. If that's true, so I squared is equal to negative 1, then I, just like 3 squared is equal to, well, no, that's terrible. Sorry. Anyways, this has to be negative 1. That's just how it is. What about I cubed? What's I cubed going to be? Well, I cubed is literally the same thing as I times I squared. And we already have that I, let me use some colors here, is the square root of negative 1. And I squared is negative 1. So I could write this as the square root of negative 1 and times negative 1, which would really get me negative I. Pause for a second and make sure that you can understand why that would be the case. It's because this one is I. This is I. It's I. You guys can see it up here, so it's negative I. Okay? What about I to the 4th? What would I to the 4th end up being for us? Well, it's I squared times I squared, which that's 2 negative 1s multiplied, so negative 1 times negative 1 is just 1. And it might be worth your time. We'll see how far down this rabbit hole we go. But if you start thinking about what's going to happen as we continue on. That's all I'm going to say on the matter, but maybe think about that. We can also do some pretty other basic arithmetic. Think about this just like if you had like 4 minus 3 root 2. You're going to end up treating this the exact same way. So we could add or subtract things. So in this case, what's going to happen is that I can take the real parts of these complex numbers, and by the by, this is the form that you're going to see complex numbers in, where there's a quote-unquote real part and then an imaginary part, and so this right here is a complex number. So is this, so is this, so is this. Anyways, 4 and 2, since we're adding here, would just get us a total of 6, and then other color, I know what colors are, it's cool. We got a negative 3i and a positive I, so that would get us negative 2i, and then this would be our combined or added sum of these two complex numbers. We can also multiply and divide. You're just going to distribute like you would do with any other thing. So we'd get a 16. We'd get a 24i. We'd get I need more colors, sorry. 10i. And then don't make a silly mistake here and not pay attention to what's going on. But here you'd get a 15i squared, but y'all already know that I squared is equal to negative 1. So this actually becomes a negative 15, which can combine with our 16. So our final answer here is going to be 1, because 16 minus 15 plus 34i. Okay, so the real story behind I is pretty wild, and it has a lot to do with math duels and people revealing stuff on their deathbeds, and it's a lot. It's a lot. And it's fantastic, but I'm gonna kind of section that off, and I'm gonna link to another video. It's pretty quick. It's only like 5 minutes, although it does lead you down a rabbit hole if you want to keep going. But it's definitely worth learning about. But for our purposes, let's see like how this might actually help us. Because if this thing, because it's degree 2, if it has to have 2 roots, but I don't see them, they've got to exist somewhere. Here's how you can find them. Ye old classic negative b plus or minus b squared minus 4ac all over 2a. That's what we need. This is the quadratic formula, of course, and the quadratic formula is going to help us by identifying where the imaginary roots for this are. I do like the idea of maybe nixing imaginary and calling these lateral, but whatever. We're going to find the imaginary roots. So in this case, a is 1, b is 0, because there's no x term, and c is 3. So we're going to get negative 0 or just 0, but sometimes maybe negative 0. It might feel nice. You never know. 0 squared minus 4 times a times c all over 2a. And what you're going to get here is you're going to get plus or minus the square root of negative 12 all over 2. Now, we can simplify the square root of 12. Some teachers will lose their minds over this. I don't really care all that much, but my guess is that the IB does. So because I can write square root of 12 as 4 times 3, and the square root of 4 just happens to be 2, then this is 2 root 3. So this is equal to 2 root 3. But hey, don't forget about that negative. So what we also have here is we have a negative 1 kind of sitting in here. Because just like I split 12 into 4 times 3, I can split negative 12 into 4 times 3 times negative 1 times negative 1. And if I squared is defined as being negative 1, then I is equal to the square root of negative 1. So I would actually probably end up writing this guy. I'm going to move over here so I actually have some space. This is going to be equal to plus or minus of 2 root 3 I, and then I'll add, of course, it's over 2, so we'll get rid of those. And so it's just the square root of 3 I, plus or minus, of course, naturally. So this is actually where I get the 2 roots. So the roots are positive root 3 I and negative root 3 I.